Let's answer this question as it was promised at the beginning of these reckless math videos about surfaces. Let's prove that the Earth is not flat. But first question that may come to your mind is this a question worthy to be answered? Because it seems as if it was a little bit silly, a little bit of a silly question. Because we have Kepler, Newton, Columbus, Elcano, I don't know, lot of great Einstein, lot of great minds that whether accepted or even proved that the Earth was not flat. So who are we to contradict them? No? And moreover, we have some clues of the Earth not being flat, being the most popular, the idea of the line of the horizon. Okay, we see when we look into the sea as ships go farther into the sea and they reach a point where they somehow start to disappear slowly till they disappear completely. That's a clue of some roundness there, okay? And additionally, in this, around this same idea, we have the idea of the higher you are, the farther you see. This is seen on ships. On ships, that's why ships have the crow's nest on the top of masts, okay, in order to have a guy there that can spot Earth before the guys that are on deck. So those clues tell us that the Earth seems as if it was not flat, okay? Even more, we are surrounded by, in popular culture, let's say, the Earth is considered round. We see it on movies, we are surrounded by images of the Earth being some kind of globe, okay? And finally, I think it can be considered by some of you a silly question. From the practical point of view, we don't need to know whether the Earth is if the Earth is flat or not. Even more, being given that the actual curvature of the Earth is very small compared to our size, or putting it in other words, the radius of curvature of the Earth is so big compared to our height. Maybe if you are lucky, you may be I don't know, 2 meters tall. Okay, the radius of the Earth is 6,400,000 meters, more or less. So, due to that difference in scale, let's say, only when very big distances are involved, we are speaking of thousands of kilometers, the effects of the curvature of the Earth start to be appreciated. Okay, and that's why for seamen, for pilots, for cartographers that are in need of calculating precisely very big distance over the surface of the Earth, the roundness or flatness of the Earth becomes important. But for us, working in distances of maybe 1,000 meters, 5,000 meters, 20,000 meters, with those distances, the Earth from a practical point of view is flat, so who cares? But this idea of the question of the Earth being flat or not being a silly question is from a practical point of view, okay? Because from a scientific point of view, we don't have to believe in Kepler. We have to understand Kepler. It's a bit of faith versus science here, okay? What do we decide to choose, regardless of our faith being very well put when we put our faith on Kepler, okay? From the scientific point of view, we need to understand to prove things. The idea of the ships disappearing over the line of the horizon may be related to an optical effect. Why not? Maybe the humidity of the air has some influence. I would need to know not only geometry, but some physics, some optics, in order to discard that possibility, okay, and say that actually the fact of the existence of the line of the horizon is a proof of the roundness of the Earth. If this is a geometrical problem, we should be able to solve it without any shadow of doubt, just by the use of geometrical concepts, okay? Then we can add that it's important to answer this question because everybody thought that the Earth was the center of the universe, let's say, and they were wrong. a bit of skepticism and a bit of critical thinking are not such a bad thing. So why not explore this question about the flatness of the Earth? And regarding this idea of why to care from a scientific point of view, from a mathematical point of view, this is a very interesting question, as we are going to be seeing right now. And it will even open a window to the resolution of other very interesting and even fascinating problems. And finally, I think that this idea about the flatness of the Earth, answering this question about the flatness of the Earth, wraps up finally very nicely what we have been seeing till now in these reckless maths videos devoted to surfaces, because we are going to be asking ourselves what kind of surface is actually the Earth. So I think that at the end this is going to be a very interesting question if we focus its answer from the mathematical geometrical point of view. So I think this is a very interesting question, as I said, and I want you to show it to you using the following argument, which I think that you will find a little bit shocking at the end, okay? If we want to appreciate the roundness of a region of a shape, what we intuitively do is we get out of the shape itself, the surface of the apple in this case, and we see if the points on that area are somehow curved around some kind of center. Okay, in the case of the sphere, we see that the whole region is curved around a single point, which we call the center of the sphere. Okay, and with an idea on how far is that center of curvature from the points under consideration, which is the radius of curvature, with the idea of how big is that distance, we get an idea of on how big the curvature is. In a line, you know that if you consider this point here on the top, you can see that here, for instance, we think that for this point the center should be somewhere around here, because it has, and we will have this radius of curvature, okay? And if I make it more open, we see that its center of curvature may be around where my thumb is, and the radius of curvature is therefore bigger. So that's how we intuitively find out what the curvature of a shape is. Getting out of the shape and seeing how far away is the center of curvature from the point under consideration. The farther it is, the less curvature there is. Somehow this is what we do when we go higher in order to see farther. Okay? What we are doing is getting actually out of the surface, and we are appreciating the border in between the shape under study and the space that surround it. Okay? And even if we analyzed how much farther do I see when I go up when I go 1 meter higher in my mast, okay, I could even start to see what the degree of curvature is. This you can see with a piece of paper with some text written, okay? You can just give it some curvature, okay? And you will see that as you go up, you will start to see more and more and more text, okay? This is the same idea. This idea of going higher, getting out of the shape, taking to the extreme, is not just a matter of going up in the mast. It's just as if we were actually going into a spaceship and seeing from the complete outside, let's say, the globe of the Earth, okay, the spherical surface that the Earth is, and we would start to turn around it in order to see how its border changes as we move around it, and then we would extract the conclusion or get to the conclusion of the Earth being a sphere. So this idea of the line of the horizon may be seen better like this, okay? As we get farther, you start to see a little bit more of text, and I am not changing the curvature of the shape. Okay. In any case, this idea of needing to get out of the surface in order to appreciate its curvature, it's related, I think, a little bit with the idea of degrees of freedom we spoke about in other video. Okay, when we move from a point to another point within the surface of the apple, we move changing our horizontal, vertical, and depth positioning. True, but once again, this is something I see because I am out of the surface. If I were in the surface as such, I would feel that I am not changing three variables in order to get to any point, but that I just need to change my north and my west positioning, let's say, some kind of vertical and some kind of horizontal positioning in order to get to any point. I feel just 2 degrees of freedom as I feel 2 degrees of freedom when moving on a piece of paper, where with just the composition of vertical movements and horizontal movements, I can get to any point. To get to this point, I move first vertically and then horizontally, or as we said, first horizontally and then vertically. But with just those 2 movements in those 2 directions, north, south, north, and east, west in the sphere, up, down, and left, right in the plane, I can get to any point. So it makes sense to feel this need of getting out of the surface in order to appreciate if it is curved or not, because with the idea of degrees of freedom is not enough. And with that, we are starting to see something which is what I find shocking about this idea of analyzing the curvature of the Earth, which is that to say something about a shape, I need to get out of the shape. And it shocks me because if it's a property, if curvature is a property of the shape, why do I need to get out of the shape? It should suffice to analyze the shape itself from inside the shape in order to say that curvature is a property of the shape and not of the shape and its surroundings. So this starts to get trickier. So let's devise some experiments, because we need to do some kind of experiment in order to prove that the Earth is not round, that don't involve this idea of getting out of the shape. Because for several reasons, but one of these reasons is because I think this may be the reason causing the rejection to explanations by members of flat society about the roundness of the Earth. Okay, so if we want to prove that something is not flat, a way of doing that is analyzing properties of flat surfaces and seeing that in the surface, in the shape under study, in this case the Earth, those properties are not met. The first that comes to my mind is that idea of straight lines. Okay, straight lines, we all agree that are the shortest way in between 2 points in space. But in a given shape, the shortest path is in between 2 points is not going to be a straight line. Okay, it's not going to be a straight line. It's going to be what we defined previously, a geodesic. Okay, for instance, the shortest path in between this point of the apple, okay, and this other point of the apple would be something like this. Okay, some kind of curved line like this, not a straight line, because a straight line will fall out of the shape. Same thing happens in cylinders. Okay, we saw that the shortest path in general terms in between 2 points of a cylinder was very easy to find just by means of saying, okay, which 2 points do you want to connect by means of its the shortest path? These 2. Okay, just develop the surface, draw the straight line connecting those 2 points, and then counter-develop, let's say, get back to the cylinder again. And that line resulting is going to be the shortest path. I think in this case it's very intuitive. And it's true as well that this line is not straight. But in planes, yes, the shortest path connecting points in a plane is a straight line. Therefore, if we prove that the shortest path in between 2 points of the Earth is not a straight line, then we will be proving that the Earth is not flat. Okay, I think this is clear, and this is what we are going to start with. Other methods, other ideas. I have thought of other 3 experiments that I am going to briefly mention here. The first one is all of them, in fact, are based on peculiarities of flat surfaces. First one is based on the idea of 2 straight lines in the plane being parallel, not only because they don't cut. Okay, if they cut, they are not parallel, but that's not the only idea that implies parallelism in the plane. Okay, in the plane, if 2 lines are cut at the same angle by another family of parallel lines, they are going to be parallel. What do I mean by this? Just what it is shown on your screens right now. The 2 black lines are the 2 lines under consideration. We don't know if they are parallel or not, but if they are cut by the same angle by a family of red lines, then they are going to be parallel. I am speaking, of course, of these angles here that, as you can see, are equal and constant regardless of which of the lines I am considering. So that idea can be somehow transposed to the Earth, okay, to the surface that the Earth is. There, the black lines would be meridians. The meridians are the result of cutting the Earth by means of planes that contain the north-south axis, the North Pole-South Pole axis. And parallels would be our red lines and are the result of cutting the Earth by means of planes that are perpendicular to the North Pole-South Pole axis. We would see then, we would discuss with our friend and tell him, okay, don't you see these meridians that from his point of view, that are geodesics, and from his point of view, therefore, straight lines. There is something very weird happening here. First thing is that you have 2 shortest paths to connect one point and another point. But besides that, and based on the fact of this parallelism definition, if they are being cut, those 2 meridians are being cut, but by all the parallels at the same angle. And from one point of view, they should be parallel. But from another point of view, they are cutting at the North and South Pole and therefore aren't parallel. Something weird is happening here, and it's due to the fact of having thought of the Earth as a flat surface. The other method, another method, which is the one we are going to be developing right now, is based on Pythagoras' theorem. We are going to find 3 points on Earth. We are going to connect them by means of geodesics. Our colleague is going to think of those geodesics as straight lines, and we are going to see that the theorem of Pythagoras is not met. And therefore, something weird should be happening there. Once again, what is happening is that he is thinking of the Earth as something flat, and therefore a surface where the Pythagoras theorem is met. And as the Pythagoras theorem is not met, it can't be flat. And finally, the other idea would be exploiting that very well-known idea of the internal angles of a triangle summing 180 degrees. Okay, we are going to see that we are able to connect 3 points by means of geodesics, and that if we analyze the internal angles, we would see that the sum of those internal angles would be above 180 degrees. And therefore, those lines can't be straight lines, and therefore we are not in on a flat surface. This can be intuitively seen here if we analyze this triangle where France, Germany, and Italy are. We see that we said before that it can be proven that the angles at which the meridians are cut by the parallels are angles of 90 degrees, okay? So this angle plus this angle is 180 degrees, plus this other angle here, it's going to be more than 180 degrees, and therefore those lines can't be straight, and what looks like a triangle, it can't be a triangle. It must be made out of curved lines. Why? Because once again, the Earth is not flat as our colleague expects. So let's develop this idea of the Pythagoras theorem. So I am going too fast. I said I was going to prove by Pythagoras right now that the Earth was not flat, but I said before that I was going to use another method, and a method that I am going to be calling from Quito back to Quito. Quito is the capital of a country in South America called the Equator, and it's in the equator, in this parallel of the Earth here, okay, which is a great circle, is of all those parallels, all those circumference resulting of cutting the Earth by means of planes perpendicular to the South Pole, North Pole axis, the one with the biggest, with the greatest perimeter, okay? So, this idea of getting from Quito back to Quito is going to play a dirty trick in the mind of our colleague of Flat Earth Society, okay? The idea is that if we are going from Quito back to Quito, looking the Earth from above, you might be looking it now, this could be, for instance, the North Pole. We are going to be describing this circumference. We're going to go from Quito back to Quito all along the equator, okay? All along the equator. That we know it's a circumference with radius, the radius of the Earth, okay? But for our colleague that thinks of the Earth as something flat, is going to be a circumference, yes, but a circumference with a different radius. With which radius? The radius, the distance at which Quito is from the North Pole, which is in this drawing, this line, this perimeter here, blah 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 blah. And that way, we are going to see that he's actually going to experience this, because we are going to ask him to walk, if he wants to, from Quito back to Quito, following a particular line, which is that of the equator. And he's going to be walking 40,000 kilometers. And therefore, according our popular knowledge of the perimeter of a circumference being its radius multiplied by 2 pi, then he's going to divide those 40,000 kilometers by 6.28, which is more or less the value of 2 pi, and he's going to find out that the number is, roughly speaking, 6,400 kilometers. And we're going to tell him, okay, now walk 6,400 kilometers, because according to your theory of the Earth being flat, that's the distance at which you are from the North Pole, okay? Because from some point of view, you are seeing the Earth like this. And he's going to walk that distance, blah, 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 and he's not going to reach the North Pole, because the North Pole is at 10,000 kilometers from Quito. It's at 10,000 kilometers from Quito. So that's the idea of this proof, okay? The only problem here is to convince our colleague that, in fact, when he is walking around the equator, or along the equator, that line is actually a circle. He may be, for some reason, suspicious. One way of proving him that what he is walking is, in fact, a circle is telling him that he is walking in such a manner that he is seeing always the North Pole at 90 degrees. And that's a circumference by definition. You may be a little bit shocked about this, but it's as follows, okay? If this is the North Pole, and we are here. What I mean by always looking to the North Pole at 90 degrees is that we are making a way like this. We are describing a path like this that is always at 90 degrees with the North Pole. So from his point of view and our point of view, both are going to be circumferences. And he's going to agree on it being a circumference, and he's going to make this division, and he's going to find that he is wrong. That no, with 6,400 kilometers, he doesn't reach the North Pole from Quito. No, walking from Quito, he doesn't reach the North Pole with just walking 6,400 kilometers. Why? Because all that we have just explained here in this slide, okay? Because he thinks on one side that he's, because he thinks that this line here is a straight line, and it isn't. And it isn't. Why it isn't a straight line? Because it's because the Earth is not flat. So that's the idea, as simple as that. These proofs sound not very satisfactory because they require a big effort, let's say, to walk 40,000 miles, to things of that sort, 10,000 miles to the North Pole, and we are so little and those distances are so big. But as I said, if we want to make an experiment to appreciate a curvature that is very little, or a radius of the Earth that is very big when compared to our size, we need to walk on distances, to work with distances that are in the range of the radius of the Earth. There is no other way, because otherwise we would need measurement instruments with an incredible degree of precision to be able to appreciate the roundness of the Earth just measuring, I don't know, 2-3 meters. We would need not the millimeter, not the micrometer, but I guess that we would even need more than that, a very big precision. So that's the way it is. The other method I devised I told you I was going to use was a method based on Pythagoras. The idea is that we are going to be drawing some kind of right triangle with the right angle on the North Pole, and then see that Pythagoras isn't met. We are going to be drawing the line that connects by the shortest path the North Pole and London. Then once again in the North Pole, we are looking now to London. We are going to turn 90 degrees in order to force this right angle in the triangle, and we are going to be walking the same distance we have walked from the North Pole to London, which is 2,680 miles, okay? And we are going to be getting to a place which we are going to be calling wherever city, and then once again, we are going to be connecting by the shortest path possible, always by the shortest path. So our colleague in Flat Earth Society thinks that they are straight lines. We are going to connect wherever city and London. Then we are going to close our wannabe triangle, and we are going to see that the distances found are not meeting the Pythagoras theorem. Okay, but here I want to speak a little bit about something else. Do we know what latitude and longitude are? Because we hear this in a lot of movies now and then, and it seems a good moment to introduce these concepts. For knowing these are very simple concepts, and you're going to get them very fast, very quickly, with ease. Okay, to know what latitude and longitude are, I just want you to picture yourselves in the insides of the Earth, in the center of the Earth, in fact, looking to the Earth from the inside and looking to a very particular point. That point of the intersection of the Greenwich meridian and the equator. That point is represented here by this cross. Okay, this is the equator passing by Quito, and this is the Greenwich meridian passing by Great Britain. Okay, their intersection is the point I want you to be looking at. And then I want you to look at any other point in the spherical surface that the Earth is. For instance, this one. Okay? To look to that point, you are going to make two neck turns, let's say. One of maybe 30 degrees and another of 60 degrees. Those turns, those degrees, are the Earth coordinates of this point. 30 degrees west and 60 degrees north. And that's the way Earth coordinates work, as simple as that. It's important to note that, do you remember that we spoke of parallels, the circles resulting of intersecting the Earth by planes perpendicular to the north-south axis. Those lines, those parallels, the equator is one of those, okay? And this is a parallel as well, this is a parallel as well. I know what I mean, you know what I mean. Parallels, its main characteristic, its main property is that all of them are at the same latitude. Sure, I don't mind. As long as my head is pointing always with the same angle up, all the points I am going to be looking at are points of a parallel, points that are at the same distance of the North Pole. All of them are at the same distance of the North Pole. And I am speaking of parallels here because of a very common mistake we all tend to make, okay? If they tell us, as we have seen so many times, this kind of projections, of maps of the Earth, if they tell us to get from London to some place in Canada at the same latitude, at the same distance of the North, in the same parallel, we all tend to do something like that, to describe this path and define this path as being the shortest one. Okay, this wants, of course, to be a straight line. That's a mistake. That if you were a sailor, in a navigator or a captain in the 15th, 16th century, trying to get your people from London to your crew from London to Canada, your crew would or die of starvation or maybe rebel and kill you, because you would be taking them by a longer path to Canada, and most likely you would run out of provisions. Okay? Maybe you don't believe me because intuitively it seems as if it has to be that line. But I am going to give you a very brief and simple proof of the line connecting 2 points, the shortest path connecting 2 points at the same latitude not being the parallel. Let's see how. So in order to make it brief, I have taken another apple. I have eaten, I think it's 3 apples since I have started these videos today. I want you to reflect on the following. We have this point in the sphere, and this is the North Pole. Okay? The shortest path from the North Pole to that point is going to be a meridian, a line passing by the North Pole, that point, and the South Pole. Okay? That I think more or less can be accepted as true. Okay? That any other path that is not the meridian passing by that point is going to be longer. Okay? Maybe this, it seems that any other path is going to be longer. If you accept this as true, you are going to be understanding this perfectly. Because now we have 2 points at the same latitude in the same parallel, the point A and the point B. And if the shortest path was the parallel, we would all agree that on the parallel being a circle with a radius smaller than that of the spherical surface under consideration. Okay? And I am going to prove you wrong that this is not the shortest path, because taking advantage of the symmetries of the sphere, I'm going to take this point A and make it now our North Pole. Okay? The shortest path from A to B, if A is now the North Pole, would be the meridian passing by the new North Pole, B, and the new South Pole. And that's a circumference with radius that of the sphere, not a smaller radius. Therefore, it's the parallel, it's not the shortest path. The parallel is not the shortest path. And I want to learn by heart the following. The shortest path connecting 2 points A and B in a sphere is that of the great circle passing by them. The shortest path in between 2 points of a sphere is the path defined by the great circle that passes by those 2 points. Or putting it into another words, the shortest path, the geodesic, connecting 2 points A and B on the surface of a sphere is that defined by the intersection of a plane passing by A, B, and the center of the sphere and the sphere itself. Okay, that's the shortest path, that circle, the great circle, sorry. So with that in mind, now yes, I can tell you in confidence that the distance from wherever city to London is of 3,650 miles by the shortest possible path. Okay, and then with those figures, 2,680 and 3,650, if you put that into the Pythagoras theorem, saying that the hypotenuse of your triangle is 3,650 and the shortest sides are 2,680, and you square them and you add them, you are going to see that it's not matching. The numbers are not matching, and are not matching by almost 1 million miles. Okay, or if you make the square root, it's going to be just 1,000, but the difference is not negligible, as you say. So another proof of the Earth not being flat. This of what our friend would think of right triangles not meeting the Pythagoras theorem. And that was all about the Earth not being flat. This is going to allow us to speak now about space-time. We will see that as we have been able to prove only measuring in Earth, not getting out of Earth, because all we have done right now is measuring in Earth, and we have been able to deduce that it is curved. Somehow this implies that in other shapes, even those of four dimensions, as space-time is, maybe those we can find out as well working somehow, detect somehow that that the space-time is curved. And if space-time is curved, nice things happen. What do I mean by this? That, as you know, shortest paths in between A and B within the sphere are great circles. But if we were able to pierce the Earth, we would find a shortest path. This idea can be explored as well in space-time. Okay, the idea if the space-time is curved, therefore somehow there could be some kind of shortcuts in between points going out of a space-time, maybe using some kind of fifth dimension. We will speak more in depth about this in the next part of these videos.